Hi, my name's Dr. Peter Kay, and this is the next lecture in the series on the internal combustion engine. My contact details are here on the screen if you have any comments, queries, or want to ask anything about in this video. So this is the sixth presentation in this lecture series. This is a brief presentation, and there's also one this week on basic hybrids. But this one I'm focusing on now is on numerical methods and how these can be applied to engine design. If you haven't seen any of the previous 5, I suggest you go and look at those first before watching this one. So in this this lecture here, I'm going to talk about numerical methods. I'm going to introduce them, what they are, why they're important, how they can aid engine design, can provide some examples of how they can be used in engineering, and I'm also going to talk about validation techniques for engines, because it's all well and good having numerical methods and clever codes that can predict things for us, but if those codes are unvalidated, then they're no use to us. Okay, so what are numerical methods? Well, the bottom line is that numerical methods develop an accurate and fast approximation, and that really is the word there, approximation. Numerical methods won't give us the final answer, but they're approximations to problems whose exact solutions are difficult to find. So there's a good graphic here. You can see the impact of this truck onto front impact, and you can see all the deformations and the stresses going through the body there. Now, if you were to try to calculate that by hand, it would take you extremely long time if you could even do it at all. And whereas with the aid of the computer, we can run these simulations very quickly. But because we do have to make a lot of approximations here, so this isn't all the rivets and welds in here aren't going to be exactly modelled. So the way that this has deformed isn't going to be exactly right to a real life crash test. But it is a good approximation, and it does allow us to cycle through some different design options very quickly to see which is the best one to then take forward for further analysis and eventually for prototyping and testing. So that's what it does do. But it's not the correct answer, and we need to be aware of that when we are simulating various things. So why do we need to learn about numerical methods? Well, starting bottom up actually. So computers are very good, they're very quick, but they're quite dumb really. All they really know how to do is to add numbers, but they can do it extremely quickly, much quicker than we can. So that's why we've exploited them in this way for numerical methods. So on top of what's controlling the computer is the operating system. So this provides a way for us to represent, manipulate different types of data. So we can look at graphs, we can run statistical analysis, whatever. Then what we've got in our operating system is the software. So this provides, whether this is a CFD code or an FEA code or whatever, this or programming language such as MATLAB, this provides the program language or platform that we use to describe how to solve the problem, and that's all it does. That's how we kind of describe the problem. We're describing the problem in the software, but the most important part of this puzzle is you, or the human. So we have the creativity and the knowledge to understand a specific problem and how to solve it. So if we were taking that truck from the first slide, we can ask the software, how is that truck going to crumple, or make us a truck that's we can ask that software to make us a truck that's strong enough to resist an impact. But what we could do is we could tell the software that we want to crash a truck, exert a force of this magnitude on this design at this speed, and the software will solve that for us, and it'll pass it through the operator to the computer, and the computer will solve it for us, hopefully quickly, and it will come back to us with the results, and then we can then interpret those results and see whether we think that design is good or not. But the software can't solve and the computer can't solve the problem of, can we make a truck that's strong enough to resist an impact? We need to set out the problem, and then the computer will solve the problem for us, and we have to interpret the answer. So what are the codes that we were solving? Well, we talked about FEA, which is finite element analysis, and that's generally used for solids, but CFD is a subset of FEA, which stands for computational fluid dynamics. And an example of this is if we're just looking at something simple such as flow down a pipe. So, we've got a pipe here, we've got flow going from left to right. There are 4 unknowns in this pipe, so we don't know the velocity in the x direction, which is, let's say, along its axis, and we're going to call that velocity u, and we don't know the velocity in the y direction, let's say that's top to bottom as you look at it, and we don't know the velocity in the z direction, which is kind of into the screen and out of the screen as you're looking at it, and we don't know the pressure each point, because there's going to be pressure gradients across here, because that's what's driving the flow. If there's no pressure gradient, we won't have any flow. So we've got 4 unknowns for the flow in this pipe, and if we've got 4 unknowns, we need to solve 4 equations. But the problem is that each equation will vary with x, y, and z, and possibly t as well. If we've got a transient flow through this pipe, it's going to vary with time. So the set of equations that govern this problem are shown on the next slide. So these are the Navier-Stokes, or part of the Navier-Stokes equations. So, and I'm not expecting you to understand this at this stage, or even solve these, definitely not. But I've just put it up here just to show the scale of the problem. So these are partial differential equations that govern. So this is continuity equations, so conservation of mass, and then we've got 3 equations, the x, y, and z momentum equations, which describe the relationship, the conservation of momentum in the x, y, and z direction. So for the flow down the pipe, we need to solve these 4 sets of equations. Now we can't do that. It's too difficult to kind of solve it in a simultaneous equation way. So the way that we need to solve this is basically to break the equations down, and then solve the equations by starting off with an assumed flow field, then looking at what happens as we step through the mesh, incrementing it at discrete nodes and discrete times, till eventually we end up with an approximation of the answer. So this is kind of an example of how that would be solved. So if red is, let's say, the exact solution, so this is the change of axial velocity through the pipe with time at the particular location in the pipe, so it says some sort of wavy function, then we can't solve at every time step without masses of computational power and time. So we can only solve the equations at discrete times, at these regular time intervals. And so the approximation, or the kind of the numerical solution that we get shown in blue compared to the exact solution in red, is quite jagged, and obviously you can improve this by decreasing your time step. So we're not getting the exact solutions, and what I've kind of tried to do on here, which might not be that obvious, that where you do, for example, here have quite a you see that this, say, velocity is changing quite quickly with time. That's when you're if your time step is too large, that's where you're going to miss information, because you won't be able to capture that fast rate of change with time. So in terms of setting up your numerical solution, you need to be conscious of the if you do have quite high gradients in your flow, then you might need a finer mesh, or if it's a highly transient flow, you need a very small time step. But basically the equations are broken down so you can solve at discrete points. So just want to kind of try and illustrate that if I can. So if you just consider the following problem. So let's say we need to build a bridge across this valley, and it just so happens that this valley makes this sort of triangle. So we've got 1 kilometre slope, another 1 kilometre slope on the other side, and the angle of the valley at the bottom is 90 degrees. So basically, if you turn this on the sides, we've got a right angle triangle. So the bridge, we can use Pythagoras theorem to work out L. So we got 1 kilometre, so 1 squared plus 1 squared square root gives us this length. So the length of this bridge should be root 2 kilometres. Now what actually is that? So we're basically saying that the length should be root 2 kilometres. So what is root 2? Well, root 2 doesn't really give you an answer, because root 2 is an irrational number, which means that it can't be expressed as an irrational number is a number that can't be expressed as a ratio of integers. So basically it's an infinite number, and I have shown what is root 2 here, and I've only shown the first 2,500 decimal places. So it's 1.4142,135, etc. I'm not going to read them out, but you kind of get the idea. Now, obviously, in terms of engineering design, we only choose the appropriate amount of significant figures, so we probably wouldn't go past this one, for example, for our problem. But I've shown this to you just to highlight that the thing that this isn't the exact solution for root 2. Someone has solved root 2 to well over, I think it's something like 117 million decimal places, and that's still not the exact solution. So I've used this example just to kind of show that actually, in terms of numerical methods, you need to think about how you're setting up the grid, what level of accuracy do you want to get from your solution for the type of problem that you've got. So in terms of numerical analysis, so if, again, using the thing of root 2 can actually be kind of expressed in this problem. So if you try this on your calculator, if you pick any number that's greater than 0, the larger the number, the more iterations you need to get to it. So if you put it into this calculator, so I started off with 42. So if you do 42 divided by 2 plus 1 over 42, you get an answer. Plug that answer back in and keep going. Then eventually you will start to converge on the 1.4. So after 7 iterations, starting at 42, after 7 iterations, you can see here that the error, I mean, that's good enough. Obviously, maybe even 60 iterations might be good enough as an approximation. So again, this is just wanted to highlight that, even when you have kind of got your equations that you're trying to solve, the number of times that you cycle through those to try and converge on your exact solution, is really depends on what level of accuracy you need, again, for the type of problem that you're trying to solve. So how can these be used in automotive engineering? Well, on basically anywhere. So I've tried to pick 6 very different examples here, and they always look quite colourful and pretty, these plots. So hydroplaning, so this is using numerical methods to work out the contact patch of this tyre on the road and how the surface water is displaced as the tyre goes over it. Aerodynamics, you probably know about. Spraying combustion, probably not so much, but this is a spray model, quite important in terms of the engine, as we talked about in previous lectures. Heat transfer, we mentioned a couple of weeks back how the temperature is distributed in certain components and how that impacts on the stress, and needs to be borne in consideration in terms of the mechanical stress as well, which is shown in here. So it's looking at mechanical stress. In-cylinder flow, so not just the aerodynamics over the surface, but fluid flow in the cylinder and in the engine block and things, how that impacts on mixing. So there is a very wide range of ways that numerical methods can be used to help improve engine design. So as I said at the beginning, it's all well and good having very clever models giving us very pretty pictures of things that we think are going on inside the engine, but if the models haven't been validated, if we don't trust the answers that they're giving us are correct, then they're of no use to us. So it's very important that we actually validate the computer models that we're using against experimental data to make sure that the answers they're giving us are representative of what's happening in reality. And I'm just going to talk about that a bit now. So just taking the point of sprays in particular. So there's lots of rigs out there where you can measure sprays in very controlled conditions. So this is just a CAD model of one. So you can see these lasers pointing in here. These lasers actually measure particle size and droplet size and velocity, and you can see a picture of the rig here. So so the results, as I say, used to validate computational codes, and laser diagnostics can be used to measure drop size, velocity, and flame fronts. So on the next slide, so I've got some basically this is the data that was taken from that rig. So you can see that this spray is impinging on this piston here, and then this is the results from a CFD code, and you can see that the results are really good. Actually, they're pretty close. They're capturing the main spray characteristics well, and so the fact that the code represents the spray in these control environments gives us confidence that then if we were to take this spray model and run it in a real but simulated engine environment, then it would also give us the correct answer under those conditions as well. So in terms of engine validation, so I mean we just showed how we can validate the models in kind of quite controlled environments, but we can also validate and also just generally gain data what's happening in cylinder by using what are called optical engines. And got a schematic of one over here. So this is the cylinder head, and this is effectively the engine block. Then what we've got here is we've got a quartz window here, which is basically extended the cylinder head up, and this is so that we can put cameras and lasers either side, so we can measure what's going on actually in the combustion chamber itself, but then also to see what's happening in parts of the engine that are hard to reach. I've actually got a quartz piston crown, and this was developed by this guy Bowditch, who he first pioneered this. So hence the piston is often called a Bowditch piston. But basically it's an elongated piston with a quartz crown on the top of the piston, and inside the elongated piston there's basically a mirror. So the camera basically looks at this mirror, which is then looking at what's happening in the combustion chamber above the piston, and so it gives us a lot of good information on what's happening inside the engine, and this can be used to validate the models, or even just get data on what's happening inside the engine. There's a good video which is based on a Ricardo optical engine that I suggest you go and watch that as well. That shows the capabilities of these optical engines and what they can do. Okay, so just to conclude then, so I talked about numerical methods, why they're important. They are, as I said at the beginning, they're very fast approximations, and approximation is the word. People see these plots and they take them for granted that because the temperature is 100 degrees there, it must be 100 degrees, but they are approximations, and that needs to be clear that they will only solve the problem that you give them. And again, that's a very important point. They can be used to solve pretty much any problem as long as we set that up correctly. And as I mentioned at the end, that there is certainly a place for validating computational codes to ensure that the codes that we are using are representative of what's happening in reality. Okay, so that concludes this brief presentation on numerical methods and how they can be applied. Again, if there's any comments, let me know. Thank you for listening.